The discovery began with a faint glow drifting through the darkness, a tiny dot that looked harmless at first. Astronomers followed it out of routine, but when they zoomed in again weeks later, the dot had grown as if something deep inside had stirred. The change was small but unsettling, because objects from other stars do not shift like this without a reason that science can explain. Whispers started to spread across observatories as experts tried to understand why the glow behaved in such an unusual way. The moment that froze, everyone came when its tail vanished and revealed a structure that did not match any comet ever recorded in our system. A silent visitor was suddenly acting as if it carried a hidden purpose, and its bright shell looked more like a mask than a natural shape. If the universe had stopped following its own rules, then what was heading toward us next? The story deepens when we return to 2025, the year astronomers detected their third interstellar object after the famous cases of Oumuamua and Borisov. At first, 3I Atlas seemed like another harmless traveler, a tiny and cold fragment drifting quietly between stars. Most experts believed it would match the pattern of older visitors because those objects were small, dim, and unable to hold heat for long periods. The moment JWST pointed its infrared instruments at the object, the expectations collapsed as the camera revealed a structure far larger than anyone predicted. Its surface released heat in patterns no natural comet had ever shown, and the glow suggested an interior that was still storing energy despite its age. Early measurements compared its size to Manhattan, which made the scientific community question how something that massive could survive the violent forces of deep space. Researchers struggled to understand how a fragment so large could travel for millions of years without breaking apart or losing its shape. The mystery grew when spectroscopic scans detected chemicals linked to heat, pressure, and the basic building blocks of life. The focus shifted from simple identification to a deeper question. If this object is more than ice and dust, then what shaped it before it reached our system? The first major twist appeared when astronomers calculated the real size of 3I Atlas and realized it stretched for hundreds of kilometers instead of the small and harmless shape everyone expected. This single measurement rewrote every assumption about interstellar objects because nothing that large should survive a journey through open space without breaking apart. Scientists compared earlier images with new infrared scans and found that the bright shell hiding the structure was misleading, since the true body underneath was massive, heavy, and extremely stable. The discovery shocked many teams because natural comets are usually fragile, yet Atlas behaved like an object built from the strongest material a young planet can produce. Its density became the next surprise when researchers studied how light reflected across the surface and noticed patterns that only appear on compact and tightly bonded matter. The interior seemed so solid that thin layers of dust and ice could not hide how heavy the core really was, and this unusual strength suggested a violent origin. Temperature readings added another mystery when JWST detected heat that refused to drop even though interstellar space should have frozen every part of the object long ago. The numbers showed warm zones spread across distant ridges, and this meant the interior had once carried enough energy to shape the terrain. No normal comet can store heat for millions of years, yet Atlas held on to it like a memory of a world that might have melted and cooled many times before its destruction. When the surface images were enhanced, cracks appeared across long cliffs while deep scars cut through valleys that stretched further than anyone predicted. Some of these cracks were wide enough to reveal darker material beneath the crust, and those shadows hinted at minerals that formed through pressure rather than slow freezing. Large mountains rose from several regions, and the peaks looked like they had been pushed upward by forces stronger than sunlight or simple impacts. Ancient basins covered other areas, and their circular shape suggested they were created by events so intense that only young planetary systems could generate them. Every detail on the surface told a story about energy, pressure, and destruction, because each feature pointed toward a world that had once been shaped by complex geology. The more astronomers observed it, the clearer it became that Atlas could not be treated like drifting debris, since its landscape looked closer to a ruined moon than a frozen rock. This changed the direction of research because the structure carried too many signs of survival to be ignored, and the surviving fragments revealed that the body had endured extreme conditions. The surprising stability of the object raised new questions about the event that created it, since it should have shattered into smaller pieces, yet it traveled through the galaxy almost untouched. Scientists began reviewing models of stellar nurseries and violent star systems to understand how a massive fragment could be launched at high speed while staying whole. These models showed that only rare situations can produce an object like Atlas because the energy required to break a planet and send its core into deep space is enormous. The more the simulations advanced, the more obvious it became that Atlas was not just surviving, but preserving secrets from a forgotten world. Every measurement hinted at a violent past, and each observation led researchers into deeper uncertainty as they tried to understand the true scale of the event that created it. If size alone was enough to break every rule we know, then what kind of power was strong enough to create such a giant survivor in the first place? The second stage of the investigation began when infrared scans revealed a rocky core wrapped beneath thick layers of ice, and the images looked strangely similar to the frozen shells of Europa and Enceladus. Astronomers did not expect to find such a structure on an interstellar visitor because comets usually contain loose dust without any organized interior, yet Atlas displayed patterns that belonged to a much more complex world. When the temperature data was compared across different regions, scientists discovered warm pockets scattered beneath the crust, and these pockets suggested that the core once stored enough energy to support liquid water far below the surface. The possibility of ancient oceans raised new questions because frozen water on that scale usually comes from planets or large moons, not random pieces of drifting ice. Minerals detected in the spectra added another mystery, since many of them form only when water interacts with heated rock, and this indicated a past shaped by environments far more active than simple freezing. These minerals included hydrated silicates and special crystalline structures that demanded high pressure, and such pressure can appear only when a world has a stable body of water buried under an icy shell. Pressure on that scale does not appear in small objects, so the presence of these materials confirmed that Atlas once belonged to something large enough to maintain deep oceans. Chemical signatures continued strengthening the theory because the object contained compounds usually found on bodies that undergo cycles of heating and cooling. The variety of molecules also suggested that the parent world existed near a hot and metal-rich star system, which is a type of environment much different from the calmer regions surrounding our Sun. These clues pointed toward a planet that was young, energetic, and filled with materials created in violent stellar nurseries where radiation shapes every new surface. The discovery changed the tone of the research because scientists realized they were no longer studying a comet but examining a fragment of a lost world that once carried its own geology. Images recorded by JWST revealed cracks shaped by internal stress, and the shape of these cracks matched patterns seen on icy moons that hide hidden seas beneath their frozen armor. Some of the deepest fractures exposed darker material that reflected light in unusual ways, and these reflections hinted at ancient vents where water and minerals once escaped. Those vents may have transported heat from the core to the exterior, and this movement of energy suggested a dynamic environment built on active processes rather than a quiet and frozen existence. The layered texture of the crust offered more evidence of change because repeated cycles of melting and cooling created ridges that curved around the body like the scars of a world that had survived long periods of stress. These scars resembled features produced by tidal forces on moons orbiting giant planets, and the similarity made researchers wonder about the star system that once shaped Atlas. If the fragment came from a place with intense gravitational interactions, then the parent world might have orbited close to a massive star or moved within a system packed with chaotic bodies. The strange chemical mix supported this idea because some of the elements required temperatures far higher than anything a comet can endure, and these temperatures indicate violent conditions that only exist near energetic stars. When all the observations were combined, the conclusion became impossible to ignore since Atlas looked exactly like the broken remains of a small planet that once carried frozen seas, active minerals, and steady internal heat. The evidence made astronomers realize they were tracking a survivor of a world that once lived, breathed, and evolved before being torn apart and scattered into the galaxy. If Atlas belonged to such a living world, then what kind of force destroyed the rest of it? The investigation entered a darker phase when astronomers examined the surface of 3I Atlas and realized it carried scars that could only be created by extreme violence. Deep craters stretched across the visible regions, and many of these craters showed sharp rims that suggested impacts powerful enough to tear apart continents on a young world. Shattered cliffs rose along the edges of long valleys, and the shapes of these cliffs hinted at sudden destruction instead of slow erosion. Some areas showed fractures that cut through layers of ancient rock, and these fractures followed patterns created when heavy objects strike a moving surface at incredible speeds. Isotopes collected from the reflected light revealed signatures altered by shock, and these signatures normally appear when rock is heated and compressed in moments of catastrophic force. Astronomers recognized that the only environments capable of producing such effects were places where planets collide or where stars tear material from their own systems. This changed the discussion completely because Atlas was no longer viewed as a calm traveler but as a survivor of a place filled with destruction. The amount of damage distributed across the body indicated that the parent world endured repeated blows during its early history. Simulations placed the object inside a turbulent star nursery where young stars form in crowded clusters, and such clusters create gravitational chaos that can throw entire worlds off course. In these dangerous environments, planets often drift too close to each other, and the resulting collisions shatter them into massive fragments. Some simulations showed a different possibility where two stars orbiting each other generate unstable gravity that stretches and compresses nearby planets until they collapse. When a young star expands or pulls material inward, it can rip apart a moon or small planet, and the remaining fragments are launched outward like shrapnel. The speed of these fragments depends on the violence of the event, and many pieces scatter into deep space where they drift for millions of years. Researchers noticed that the patterns on Atlas match those predicted for objects hurled from binary star systems, and these predictions supported the idea that the fragment came from a violent stellar interaction. Binary systems often generate intense gravitational waves that break apart fragile surfaces, and the scars on Atlas reflected this type of sudden stress. Other marks indicated that the parent world might have orbited close to a massive planet, and this proximity created tidal forces powerful enough to weaken the surface before it broke. The combination of shocks, pressure, and tearing formed surface patterns identical to those produced by destructive celestial events. When these details were studied together, a picture emerged of a world that had once existed inside a dangerous system where gravity and heat shaped every moment. One simulation showed a young star pulling a smaller body inward until it cracked from the pressure, and the fragments from that body scattered across the system. Astronomers suggested that Atlas might be one of these fragments, and its stability revealed that it came from the deepest and strongest part of its original structure. The survival of such a fragment required unusual density, and this density came from the compressed core of the lost world. Because of this, Atlas remained whole, while other fragments likely broke down into dust long before reaching interstellar space. Researchers realized that the fragment's path through the galaxy was not accidental because only the strongest pieces travel far enough to meet distant star systems. Many fragments lost energy or collided with other bodies, but Atlas stayed intact and continued its journey through cold and harsh environments. This remarkable endurance made scientists wonder how many fragments from destroyed planets roam unseen across the galaxy. Among all the pieces launched into space by the violent destruction of the parent world, Atlas was the one strong enough to survive long enough to reach us. The mystery surrounding 3I Atlas deepened when JWST detected chemicals that had no place on a drifting fragment of ice, and the discovery forced scientists to rethink everything they believed about interstellar objects. The first major surprise appeared in the form of nitriles and carbon chains that are normally found in environments where complex reactions take place, and these reactions often produce molecules linked to amino acids. Such molecules require specific temperatures and stable sources of energy, and those conditions rarely exist on bodies that wander through cold and empty space. JWST confirmed the presence of PAHs, and these compounds form in regions shaped by high heat and radiation, suggesting a past filled with powerful forces that shape the chemistry of the fragment. These molecular clues pointed toward a world that once experienced cycles of warmth and cooling, and these cycles hinted at a place where water and rock interacted repeatedly. The spectra contained fingerprints associated with hydrothermal activity, and these fingerprints mirrored the signatures found near the deep ocean vents on Earth, where extreme pressure and heat create unusual compounds. Hydrothermal reactions require a stable heat source beneath a thick shell, and this condition is usually present only on large moons or small planets with active interiors. The identification of these signals implied that Atlas had once carried enough energy to support underground activity, which challenged every expectation about its origin. Some of the most puzzling findings came from the dust escaping through cracks on the surface, and this dust carried isotopes from a metal-rich region of the galaxy that lies far from our own. Isotopes created in such places often contain higher concentrations of heavy elements, and these heavy elements are produced only in star-forming zones filled with intense radiation. The dusty material showed clear signs that it did not belong to a cold and quiet environment, and this forced researchers to search for new explanations for the object's formation. The strange mixture of elements indicated that the parent world existed near a powerful star where radiation and heat shaped the landscape, creating compounds rare in our system. This metal-rich environment gave the fragment a unique chemical identity, and this identity resembled the chemistry of worlds formed in younger and more energetic regions of the galaxy. The presence of these exotic molecules suggested that the lost world endured extreme transitions, and these transitions created a surface rich with chemical diversity. Scientists noted that although the object was not alive, it carried several ingredients required for the early stages of life, and these ingredients remained intact despite the harsh conditions of space. This raised the possibility that the fragment preserved sensitive molecules through its long journey, and such preservation required unusual stability and a strong protective crust. Some researchers proposed that the mix of heat, pressure and minerals once created environments that resembled the early Earth, which increased interest in the object's geological past. The idea gained traction when simulations showed that the parent world may have hosted ocean floors with hot vents similar to those that support hardy organisms on Earth. These vents produce reactions that build complex carbon structures, and those structures become the foundation for more advanced chemistry. If Atlas carried traces of such reactions, then the fragment represented a rare opportunity to study the earliest conditions that can lead to life. This possibility encouraged the theory that interstellar fragments may act as couriers across the galaxy, transporting molecules that support biological growth. The discovery shifted the discussion from simple survival to the role of wandering debris in shaping new worlds, and this possibility deepened the sense of wonder around the object. If the chemistry of Atlas reflects the earliest steps toward life, then what does that mean for the galaxy as a whole? The final stage of the early analysis began when scientists realized the crust of 3I Atlas behaved in a way they had never seen on any interstellar object, and this unusual behavior opened a new line of questions about its survival. Observations showed that the outer layer slowly sublimates as sunlight warms the surface, and this process releases gas into space while thinning the ice. However, when the temperature drops again, the escaping moisture refreezes and forms a new shell, creating a self-healing layer that protects the interior from further damage. This repeating cycle acts like a natural shield that constantly rebuilds itself, which would explain how sensitive materials inside the object remain preserved despite exposure to harsh conditions. The self-repairing crust reduces the effect of cosmic radiation, and this allows delicate molecules to survive long enough to provide clues about the fragment's distant past. Internal heat pockets offered another puzzle because they remained active even though the object spent millions of years drifting through icy space. These pockets trapped warmth deep below the surface, and the heat prevented the interior from freezing into a solid mass. The survival of these warm regions suggested the presence of minerals that store heat efficiently, which supports the idea that the object came from the compressed core of a once active world. This trapped heat also kept the internal structure stable by preventing extreme temperature swings that usually fracture frozen bodies. Maps of the rotation added a new layer of mystery when they revealed ice cliffs and dangerous ridges that rose sharply from the surface, and these features looked frozen in the middle of violent destruction. Deep fissures cut across the terrain, and many of these fissures opened into dark cavities that might have once carried flowing material before the world was torn apart. These structures resembled the damaged remains of a world caught in a catastrophic event, and the frozen debris looked as if time had stopped at the moment of impact. Scientists noticed that the formation of these cliffs required internal pressure, and the presence of such pressure hinted that the object once possessed enough gravity to push material upward. The existence of these raised formations supported the idea that Atlas came from a world large enough to develop strong geological forces. The surprising detail was that these structures did not crumble during the long journey across the galaxy, which meant the fragment remained unusually strong. Cosmic radiation usually breaks down complex materials, yet Atlas remained chemically active, and this activity suggested slow reactions were still taking place beneath the crust. The persistence of these reactions indicated the presence of energy sources that continued operating long after the parent world was destroyed. Such endurance showed that the fragment carried more than ancient debris because the chemistry inside it resisted decay far better than expected. Some researchers suggested that the structural strength came from the high concentration of heavy elements, which made the body more resistant to fractures. Others argued that the self-regulating crust acted as insulation, which shielded the core and reduced the temperature loss that normally destroys fragile materials. This combination of stability, heat retention, and unusual protection formed a system unlike anything seen before, and the object seemed designed to endure extreme environments. Every new observation forced scientists to reconsider earlier assumptions because the survival of such a large fragment made little sense when compared to other interstellar objects. The evidence suggested that Atlas did not simply resist destruction, but adapted to it by regenerating its surface and preserving heat. A fragment this intact should not have survived for millions of years, which means something about Atlas is still protecting it even now. Atlas ends its story as something far greater than a comet because every measurement shows it is a massive shard from a lost world shaped by forces no longer active in our part of the galaxy. Its chemistry carries the fingerprint of a distant star, and the minerals inside it record the rise and fall of a planet that lived long before our sun was born. This drifting fragment forces us to rethink how worlds form, collapse, and travel through the dark because it proves that planetary history does not end when a system dies. Now every new scan brings Atlas closer to revealing the final layer hidden under its regenerating crust, and the next observations may expose the last piece of its past. If this is only one survivor from a broken world, then how many more are moving silently through the darkness, waiting for someone to notice them?